Today we're going to work on our second part of this lesson with confidence intervals for a proportion. Today we're going to look at actually constructing the confidence interval, and this is based off of the rule for sample proportions that we looked at last week. So if you recall from that rule for sample proportions, if you're taking a bunch of samples of the same size, then these samples will all fit into a normally distributed curve that's approximately bell-shaped. The mean, the center of that curve, will be the true proportion from the population. And the standard deviation will be found using this equation that we worked with last week, where you're taking the square root of that true proportion times its complement, 1 minus that true proportion, divided by the sample size. And recall from the empirical rule that in 95% of all samples, the sample proportion will fall within 2 standard deviations of the mean, which is that true population proportion, P. We talked a little bit about that in our previous lesson, that you could have different levels of confidence. One standard deviation above and below would be 68%, 3 standard deviations would be 99.7% confident, but 95% is a little bit of a good compromise, a good balance of those two. It's a high level of confidence, and it's a decently wide margin of error. We'll talk more about that at the end of the lesson today. Now, the issue here is that we're using the population proportion as both the center of this curve and as part of our calculation for standard deviation. But if you think about it, the whole purpose of taking a sample is because we don't know what's actually happening in the population. So what we're allowed to do, and this is proven to be true as part of a bigger idea called the central limit theorem, is it allows us to substitute in sample values instead of that population value. So we're going to substitute in the sample proportion for the true proportion in that formula for the standard deviation. So that means that instead of having sigma as our population standard deviation, we're really just going, not sigma, because we're not working with standard deviation. Instead of P, the population proportion, we'll be using P hat, which again represents a sample proportion. We haven't looked at it directly here, but on the top of each of these lesson pages, you have a link to our equation sheet for these sections. And on that equation sheet, it's emphasized the difference between the notation for the population, which would be P, population proportion, and for the sample, P hat. Okay? Now, you're taking that sample proportion, P hat, and much like margin of error, because this is essentially the same thing, you're going 2 of these standard deviations above and below. So plus or minus 2 standard deviations creates that 95% confidence interval. Now there's a little technical note here at the bottom. We use 2 standard deviations, but technically if you were to look at the z-scores, 1.96 standard deviations would give you 95% confidence. You have 95% in between, but 1.96 close enough to 2, and it just makes it so much easier if we just multiply by 2 instead of 1.96. But in the future, you might see 1.96 instead of 2 if you're calculating a confidence interval in a future course. So let's take a look at a few examples here. We've seen some of these problems over the last few weeks. Oops. We saw an example where we're looking at if the wife is taller than the husband. It took a random sample of 200 British couples. The wife was taller than the husband in only 10 couples. So that proportion, p hat, is 10 out of 200, or 5%. We can calculate the sample standard deviation here by using our equation, square root of p hat times its complement, so 0.05 times 0.95 divided by 200, take the square root of all of that. We get a standard deviation of about 0.015. Now to calculate this confidence interval, we multiply by 2, because 2 standard deviations below, 2 standard deviation above, which makes this value that we're adding and subtracting a nice value of 0.03. Okay, so if we were to visualize this on our bell curve, we've got our sample proportion, which is representing the population proportion of 5%, right there at the center, 0.05, and then 2 standard deviations below, 2 standard deviations above to create that 95% confidence interval. We subtract 0.03, making this 0.02. We add 0.03, making this 0.08. So our 95% confidence interval is interpreted as we are 95% confident, excuse me, that between 2 and 8% of all British couples, the wife will be taller than the husband. All right. Now, again, that has some inaccuracy built into it. We'd expect 5% of the time, or about 1 in 20 times of taking these samples of 200, that we would have the proportion of British couples where the wife is not taller than the husband between outside of that 2 to 8% region. Here's another example looking at ESP, extrasensory perception. And this was done where the subject tried to guess which of 4 videos the sender was watching in another room. Okay, so there's a 1 in 4 chance that just by guessing alone, the person would guess this correctly. So we found that in this case, actually, of the 165 cases, 61 of them resulted in successful guesses. So our p-hat calculation, 61 divided by 165, gives us our sample proportion of 0.37, 37%. Standard deviation, you can see that calculation, 0.37 times the complement, gives us, divided by 165, take the square root. There's our standard deviation, multiplied by 2 to create our confidence interval, 0.37 plus or minus 0.08. We are 95% confident that the probability of a successful guess in this situation would be between 29 and 45%. Now, we compared this to a majority or minority in our previous lesson. We knew that we'd expect, just by guessing alone, that we would be right 25% of the time. If you're guessing 1 out of 4 chances, this confidence interval is entirely above 25%. So that's beyond what we would expect to have happen. So we'll be using this idea to look at if that difference is significant enough in our sections coming up. Our last example here, looking at people who are quitting smoking using a nicotine patch. There was a study of 120 volunteers randomly assigned to use a nicotine patch. After 8 weeks, 55 of them had quit smoking. So our p-hat calculation, 55 over 120, gets a sample proportion of 46%. So you can see standard deviation calculation, multiplied by the complement, divide by 120, take the square root. Here's our sample standard deviation, multiplied by 2 to create the 95% confidence interval. So 46% plus or minus 9% takes us a confidence interval. We are 95% confident that between 37 and 55% of smokers treated this way with a nicotine patch would quit smoking after 8 weeks. Now, for a comparison, there's a placebo group, and their confidence interval was 13 to 27%. So think about that comparison. With the nicotine patch, 37 to 55% percent of the users quit smoking after 8 weeks. That's entirely above the placebo, which gives some credence to the fact that this nicotine patch is more effective than the placebo. So I mentioned earlier that I would say 99% of the time you would see a 95% confidence interval being used. But if you wanted to use a different level, we saw with the empirical rule, you could be 68% confident, meaning that about 2/3 of the time that true population value would fall in that confidence interval. That's not a very high level of confidence, though, even though your width of the interval is going to be pretty narrow. Okay? The other one, 99.7%, that sounds really good. That's really close to 100%. However, the problem with that is that's going 3 standard deviations to the left and 3 standard deviations to the right. So you're going to have a pretty wide interval there that's not really all that helpful to say that you're 99.7% confident that your value is between these two extreme margins. So I said 95% confident is a pretty good balance of those two. It's a pretty high level of confidence, and the width of that interval is respectably average. Other values that you might see, but they're not part of the empirical rule, would be 90% level of confidence and 99% confident. Those both sound good, but they're not integer standard deviations away from the center of that curve. So you could use those confidence levels. We saw the one in our previous lesson with the EPA talking about secondhand smoke. They used a 90% level of confidence to avoid dropping below 0. But you could do those, but the calculation is just a little bit more complicated because it's no longer an integer that you're multiplying by. We've talked about margin of error, and remember the equation for margin of error was 1 over the square root of the sample size. It's a quick and conservative way to calculate something, but you could look at this derivation based off of the equation for a 95% confidence interval. The two equations for a confidence interval and the margin of error are equivalent when the proportion used for the standard deviation is 50%. Now, a lot of times that's not actually true, but this gives you a case where the two are equivalent. Margin of error, 1 over the square root of n, that's a quick way to get an idea of what that confidence interval would look like. But if you wanted a more accurate example, you're better off using that full confidence interval equation with the sample proportions. Our last idea here is to look at a quick case study. This is a case where we don't typically have what's actually going on in the population. Okay? Again, the purpose of taking a sample is to avoid having to do a full-blown census, which we've said is very painstaking. A lot of times your resources, like your time and your money, are better spent getting an accurate random sample. But there are certain cases where a census is required, and this is a kind of interesting example from the 1980s where we see that. The Sears Company erroneously collected and paid city sales taxes for sales made to individuals outside the city limits. So that's kind of like in Allegheny County, we have an extra 1% sales tax as opposed to the rest of Pennsylvania as being 6%. Except for some counties in Philadelphia. So if you were to buy something in Washington County, you're only charged 6% sales tax, but if it's at a store in Allegheny County, you're charged 7%. So it's something kind of similar going on with Sears, and Sears took a random sample of the sales slips for the period in question to estimate the proportion of all such sales that they owed money in back taxes to. The 95% confidence interval for the true proportion of all sales made to out-of-city customers was about 36.7%, plus or minus 3%, giving us a confidence interval between 33.7 and 39.7%. Okay, 33 to 39% of the customers were owed reimbursements for their erroneously charged sales tax. Now, to estimate the amount of tax owed, they multiplied that percentage by the total tax they had paid. You can see almost $77,000. The result was about $28,000 with a 95% confidence interval. Okay, you take these percentages and you multiply them by these dollar amounts, you get your value in that you would owe from almost $26,000 to about $30,000 on the upper end. Now, the problem was that the judge did not accept the use of sampling and required that Sears go back and examine every single sales record. So, because this was the court saying they had to do this, they went back and they calculated $27,586 is what they owed in sales tax. Look at that value in comparison to the confidence interval that they calculated. Pretty much exactly in the middle, $27,000 between those values that they found. Okay, in fact, they were going to pay a little bit more. They were going to pay $28,250 in back taxes. Now, this was required by law. The sampling method gave them a pretty accurate estimate for the total amount that they were owed. Okay, but look at the time and money that was spent going into this. It took Sears about 30 person hours rather than man hours to conduct the sample, but it took them more than 10 times that amount, 3,384 hours to do the full-blown audit, which is like a census. So the money that they spent performing that audit well exceeded what they were going to do with that sampling method, but the fairness is that the judge was just following what the law said, that the sales tax return required a sale-by-sale computation. And this is similar to what we've talked about with our national census. We know that we're kind of going through that right now. That's required in our Constitution, that a full-blown census be done every 10 years. And we've said that oftentimes if you just get a well-done randomized sample, that could be much more efficient in terms of time and money, as you can see in this box right here. But sometimes a complete audit is required.